Recording. All right. Good morning. Happy post Halloween. Hope it was good. We left off with an example and I said, how about you wrap this up on your own and then we'll pick up from here. And that is exactly what we'll do. So continuing from last day, week even. Where were we here? You might want to review. So I'll just read from here because I have way too much text, but it's supposed to be a recap. It wasn't really, it was kind of big. But so what we do, our first steps, good morning. For a hypothesis testing question is, of course, we have to state the null and alternative hypotheses, which we did for this question that we're working on. And then we're going to do the test. Now that can take one of two directions, and we're focusing on the confidence interval for now. And then later today, hopefully we'll get to talking about the test statistic, which is the p-value approach. Then step 3 is I'm kind of generalizing and calling it gather evidence. So in terms of if we've built a confidence interval, so we're going to focus on this stream right now, we want to see, is the null value contained in the interval? Okay, and so we can handle this. We can do that, right? We can check to see if the null value is inside the interval or not, right? Then in terms of our conclusion, okay, if the null value is contained in the interval, then we do not have enough evidence to reject H naught, right? Because then it is a plausible value for the population proportion, right? Whereas if it's outside the interval, then we have evidence against the null hypothesis, right? And so just remembering that there's if we built a 95% confidence interval, which is the default, then there's always a 5% chance that we're wrong, right? So we need to remember that. And here I emphasize, and I'm going to emphasize it again, we can't say we accept a hypothesis, because we always want to leave it open that, okay, well, we could be wrong because there's a 5% chance that we're wrong. We're 95% confident, but there's a chance that we're wrong. So if the null value, it's catching up here. Wow, it's slow today. So annoying. If the null value is not in the interval, right, then we have enough evidence to reject H naught in favor of HA. Okay? So our conclusion is going to be broken down into 3 parts, okay? And so the first part is checking whether the null value is inside the interval or outside the interval. Then we can draw our conclusion in terms of the null hypothesis. And so there are really only 2 options here. We either have enough evidence to reject H naught, or we do not have enough evidence to reject H naught. Okay, and so we do all our testing assuming the null hypothesis is true. So that's why our conclusion has to be in terms of the null hypothesis. So finally, right, you have to state your conclusion in terms of the question. That's why we're here, right? We want to answer a question of some sort. And that's the one that people tend to forget, because at this point, you've done a ton of work, right? And you're exhausted and you don't want to work on this anymore. So then you forget to tell me the conclusion in terms of the question, but that's arguably the most important part. So we were working on this example here. So I'm just going to grab it, do a little grab and go here, paste as an image, yes. Okay, I'm gonna see if I can, just about. All right, I'll just do this. Copy. How about, because I don't want it to take up a ton of space on your page, because you already have this presumably in your notes somewhere. Okay. Oh. Well, this is annoying. Whatever. I'll leave it big. And then we did our calculation. Copy. That arrow actually kind of worked out, but oh well, I already ditched it. And whoa. And then I said, we'll finish up next day. Okay, so this is where we got to last day. So this is all from last day. Okay. So what we found was we had, and maybe I'll make this a little bit bigger because it kind of looks weird. Like that. I don't know. We had a question, right? And we're trying to see if there's been a change since 1999 in the percentage or the proportion of Canadian adults who have an RRSP, right? And so we said, okay, well, we know from 1999, we were told that it was at 57%, right? The proportion was 57%. So that's the value that we want to compare our sample proportion to. So that's what goes in our null hypothesis, okay? And I would argue that setting up your null and alternative hypotheses are potentially the hardest part of these questions, because what you're going to see is that's when you decide what type of question you have. So far, we've only dealt with one type of question, a one sample proportion. But later, we're going to build up a library of different types of questions that we can deal with, right? And so we need to be able to identify those types. And then we need to be able to set up the null and alternative hypotheses for those types as appropriate. And so that's probably the hardest part. Once you've decided what type of question you have, then you're off to the races. Then there's really only one path that you can go down for each of those scenarios. Okay. And so we set up our null and alternative hypotheses, right? And we're assuming that the proportion, the population proportion, is 0.57, unless we find proof otherwise, right? And so then we built a confidence interval, and our confidence interval is built around our point estimate, our p-hat, and we use the table, the t table, table C, let's call it, to find the Z star, the critical value. And then we built our interval, making sure that you first subtract the margin of error. And so just as a quick reminder, right, this here is the margin of error. Okay. So first subtract the margin of error to get the lower bound, and then add the margin of error to your point estimate to get the upper bound, right? That it's important that you list them in an appropriate order. So now we have to interpret this interval, right? We are doing a hypothesis test, but it helps if we start interpreting these intervals. So interpret the interval Okay, it's optional for hypothesis testing, but it doesn't hurt to kind of interpret it to get some practice, right? So interpret the interval, optional for hypothesis testing. It's not optional if the question is asking you for a confidence interval, then you have to interpret it, right? Often I'll try to say something like interpret the interval, just to remind you that you have to do that. But otherwise it's understood. You have to interpret your interval. You can't just leave it. Okay. And so what would we say? Well, we built a 95% confidence interval, and it is for the true proportion of Canadians 18 years of age or older. I'm going to shorthand that to adults. Canadian adults who have an RSP in 2012, right? Because that's where our sample came from. So what we say is we are 95% confident the interval from 64.1% to 69.9%. Yeah, exactly. So yeah, so the key thing is that the population proportion for the proportion of adults, Canadian adults who have an RSP or had one in 2012, it exists. We just don't know what it is. So we're trying to figure out where it might be. And so that's why we're only 95% confident that it's somewhere in this interval. Yeah, an assignment type question, exactly. Because it's so important. It's so easy to misinterpret these intervals. So you want to really stick with it until you're like, okay, the population proportion is fixed. Okay, so that's the key aspect. So we're 95% confident that the interval from 64.1 to 69.9% captures. And I love using the word captures because it really signifies that this thing is fixed. I'm just kind of going blind and trying to figure out what it is, right? And so I don't know if it's been captured or not, but I'm 95% confident that I have. Captures the population proportion of Canadian adults that had an RRSP in 2012. Okay. So that part's optional, but I hope that as soon as you've built a confidence interval, you feel that urge to interpret it. So that's what we're doing. So once we have the interval, then step 3 is, I'm going to call it gather evidence. Usually I just call it find the p-value because that's what we do with the p-value approach. But with using a confidence interval, I had to find a more general term. And so step 3, I'm going to say gather evidence. Okay. Now, if I'm 95% confident that the true proportion is somewhere between 64 and 69, right? If I go back to my null hypothesis, well, what I'm actually saying is that I'm 95% confident that this is not true, right? P can't be 0.57 if the interval goes from 64 to 69, right? And so what we can do is we can look at this interval, and remember, we're just on a number line, right? And so what we can do is we can look at this kind of interval here, and our confidence interval is from 64.1% to 69.9%, right? This is our 95% confidence interval. Okay. What we see is that if we look at this number line, and now I've forgotten our hypothesized value, 0.57. I'm going to try to not scroll so much because it's so slow. Man, oh man. 0.57. So what I do is I look and I see, is it in the interval or not? So 0.57 is somewhere here. This is our null value. Okay. So there's a 5% chance that this interval is not reflective of the population, but I'm 95% confident that it is. So I'm going to take those odds. And so here, this gives me evidence that the interval is above the null value, right? Or rather, the null value is not contained in the interval, right? And so this gives me evidence to reject the null hypothesis, right? Because this null value is not in the interval. Since the null value is not contained in the interval, we have enough evidence against H naught, right? We have enough evidence to reject it. We have enough evidence to reject H naught. That P is 0.57. Now, we've seen how the intervals move around, and even if we have a representative sample, there are situations where we have samples that are kind of way off into the tails, right? And so that happens, and that's why we're just building 95% confidence intervals. But we're still pretty confident. So this part, comparing the null value to the interval, is it in the interval or not? That's actually part of our conclusion. So I'm going to restate it as part of the conclusion, and then only this here where I compare it, compare the null value to the interval, that's going to be our the gather evidence portion of it. Okay. So this is part of the conclusion, right? It just didn't look like we had much in this section for step 3, if I didn't say it, right? But here we're outlining why that is, why we have gather evidence. So why we have evidence against H naught. So now for step 4, is our conclusion. Now our conclusion is going to be in 3 parts, right? We have to touch on 3 parts, and I'm going to put it into a sentence, and then I'm going to pick apart the sentence so you can see what that means. So usually I would just argue with this, since the null value is not contained in the interval, right? You're going to say whether it is in the interval or is not in the interval, right? And so since the null value is not contained in the, let's show off a little bit, 95% confidence interval, we have enough evidence to reject H naught. We have enough evidence to reject H naught. And if you're rejecting H naught, then you're rejecting it in favor of HA. In favor of HA. you can see how this is pretty generic, and it's not in reference to the question at all, right? So if you've been hired to do this analysis and this is all you've submitted to your client, they would be pretty peeved. So what does this mean? This is why, someone's getting you to do the analyses for you or for them. So what does that mean in terms of the question? It means that the proportion of adults who have an RRSP is different in 2012 than it was in 1999. Okay, but usually what I do is I take the question and I reword it as an answer as much as I can. So is there evidence that the proportion of Canadian adults who have an RRSP has changed since 1999? There is evidence that the proportion of Canadian adults who have an RRSP has changed since 1999. Okay. Therefore, there is evidence that the proportion of Canadian adults who have an RRSP has changed since 1999. 1999. I can't help it. I know you guys are singing it too. So let's highlight the different parts here, right? Arguably, this conclusion in terms of the question, that's the most important part, right? But first part that we have to handle is the null value contained in the confidence interval? All right. So that's kind of part one of the conclusion is compare null value to the interval. Then we move on to part two. Based off of that, do you have enough evidence to reject H naught? So I'm going to summarize that as the conclusion in terms of H naught. So part two is the conclusion in terms of H naught. And then finally, the conclusion in terms of the question. So part three, conclusion in terms of the question. Yeah. Nice. So these hypothesis testing questions, they feel overwhelming, especially in the beginning. But as long as you just follow the same procedure, you'll be able to pick your way through and you'll start to see the patterns soon enough. Okay, and we're going to do tons and tons of different types of confidence intervals and hypothesis testing. So we're going to feel really comfortable with it by the time we're done with it. I know it doesn't feel like it in the beginning. But wait, there's more ins and outs. Okay, so I want to start talking about using the p-value approach, which is considered a more formal approach, although most statisticians are kind of leaning towards just using confidence intervals because it's, I don't know, a little bit more flexible. And so you'll see what I mean. But so confidence intervals are kind of new age, if we're going to do that for hypothesis testing, but there are a couple of shortfalls. For example, we can only talk about whether there's been a change since 1999, right? Even though from that interval that we drew out, we can see that, okay, it looks like it's actually increased, right? But because we're making an interval, a 95% confidence interval, then we can only talk about a change. So that's a shortcoming of using a confidence interval. So one shortcoming of using a confidence interval to do a hypothesis test, is that we can only look for a change. We can only detect a change. Is that we can only detect a change, right? Which is basically something that says the alternative hypothesis. Yeah, you're welcome. 1999. So what we're saying is, okay, we can only use a confidence interval if we have this not equal to sign in here. So in our alternative hypothesis, right? So this is how we show that we're looking for a change, right? Whether it be up or down, it doesn't matter, just one direction or the other. And we're not going to distinguish between those two. Okay, so we can only detect a change with a confidence interval. So that's where the p-value approach comes in, and it's a little bit more formal, and it'll let us detect if the population proportion is less than some value, or in our case, what we saw was that the population proportion in 2012 has actually increased from 0.57, which was the population proportion in 1999. I said it all plain, right? And so if you want to test one way or another, so making it a one-sided test versus a two-sided test, right? Then we're going to need p-values. You can test the two-sided test with p-values as well. So we're going to have a look at that. And so here, just as a note, we call this a two-sided or two-tailed, doesn't matter, test. Okay, and the reason for that is because we built this interval. So if we think about a normal distribution, we've got 95% in here, and then we've got some percentage here in the tail. Of course, that's 5% split evenly amongst the tails. So that makes 2.5% in each tail. Okay. So the problem is using a 95% confidence interval, we already said, well, there's a 5% chance that we're wrong, right? And that would be an error, right? And so there's names for those errors that we could be making. And so let's talk about type 1 and type 2 errors, right? And we'll talk about the different mistakes that we could be making that we don't know that we're making, because we have to assume that our data is good, right? But we know that we could just have a rogue sample that's not representative of the population, even if it was collected correctly, right? And so in building a 95% confidence interval, we understand that there's a 5% chance, I guess, 5% probability, no, 0.05 probability that we're wrong, right? And so in building a 95% confidence interval, there is a 5%, I hate to use the word chance because it's not very telling, but there's a 5%, you know what, let's say probability. Right, or 0.05. Probabilities are decimals. That's my holdup. I don't want to talk about percentages as probabilities, but that's fine. They are. But I want you to see the 95 to 5, so that's why. So in building a 95% confidence interval, there's a 5% probability that we're wrong, right? That we are wrong, right? Wrong in rejecting H naught, for example, right? In the previous case, there's a 5% chance that we shouldn't be rejecting H naught, that the population proportion is 0.57, or it came from a population where the proportion is 0.57, and we just happen to see an extreme result. That's one of the scenarios that could have happened here. So we need some way to talk about these errors that we could be making. Okay. So we need to discuss the errors. Oops. I love combining words, it turns out. Whenever I write, I always like combine words. It's weird. The errors we could be making. There are only two. They're called type 1 and type 2. And what are they? Well, let's outline our different scenarios here. I can either reject H naught, or I'm going to say fail to reject H naught, because you never want to say accept, right? We talked about that. But in terms of the conclusion, so my conclusion, let's say, is that I either reject H naught or I fail to reject H naught. Those are my two options, right? And so I don't know which one is correct and which one is incorrect, but there is some truth out there, right? And so here, maybe I should use a different color for these guys. Style. So there is some truth out there, right? We just don't know what it is. And so the first option, and let me just match my, well, I already screwed up the one I had jotted down here for reference. I always have to make this table, otherwise I get confused, but looks like I already mucked it up. So that's okay. H naught is true. Whoops, that should say true. That's the first option, right? Or H naught is false, right? And just to separate these, we'll use little blue lines here. And what the hey, let's just square it up here. Make a nice, weird looking table here. Yeah, things got weird, but that's okay. So I can't stand it. It's part of the table now. Okay, so if H naught is true, then the correct conclusion would be that I fail to reject H naught, right? So if H naught is true, then If I fail to reject H naught, meaning I don't have enough evidence to reject it, right? Clearly avoiding the word accepting, right? I don't accept anything because there's always a chance that I'm wrong. And so this one, that would be the correct conclusion in that case, right? If H naught is false, then the correct conclusion is that I reject it. I reject it in favor of the alternative hypothesis, right? So these two are good. Those are the correct conclusions. And we don't know if we've made the correct conclusion. So we need to talk about, okay, what are some of the mistakes I could be making? Now, when H naught is true, and you've rejected H naught, right? So that means that saying that the population proportion is different has changed from 0.57 when maybe it hadn't, right? Maybe it was from a population of 0.57 with a proportion of 0.57, right? And so this is what we call a type 1 error. And I'll even do it in red, kind of jarring here. Type 1 error. Okay. So the type 1 error is the one that we're most concerned with, and that's the one that we're able to control. How can I control it? Well, we said that if I make a 95% confidence interval, there's a 5% chance that I'm wrong, right? There's a 5% chance that I reject H naught when I shouldn't be rejecting H naught, right? And so we can control that 5% by changing our confidence interval, right? I could decrease it to 1% if I made a 99% confidence interval, right? 2% if I made a 98% confidence interval, right? And so we can control the type 1 error rate, okay? The one that's harder to control is the type 2 error. And so that's when we H naught should be rejected because it's false, but we didn't, right? We didn't find enough evidence to do that. Now, usually the only way that we can control the type 2 error rate is by increasing our sample size. That's all we are going to have in this course, right? And so we'll call this a type 2 error. Okay. So type 1 error, we can control the error rate, the type 1 error rate, by changing our confidence interval. Okay. We can control the type 1 error rate by changing the confidence interval, or the confidence level, I should say, by changing the confidence level, right? So if I make a 95% confidence interval, then we said that there's a 5% chance of being wrong, right? So 5% chance that I'm going to reject H naught when it's actually true. It is supposed to be on that same curve as the 1999 folks, right? And so there's a 5% chance of making a type 1 error. So the 5% is the type 1 error rate. We usually call this the alpha level, okay? And so the type 1 error rate is denoted by alpha. Oops, should make that a little bit cleaner. That's that Greek letter that looks like a fish. That wasn't a very good one, was it? I can do it. There. that looks more like a fish than an alpha. It's supposed to have like a little bit of an A scrunch, but it's okay. I think you get the idea. But so this is an alpha. Whoa, huge. So we were, that's what people are getting carried away in the chat, and oh, the alpha level, yeah. And so here we are, not that bad, right? Sounds scary when you first hear it, but it's not bad. Okay, and so the alpha level is really just the probability of making a type 1 error. Okay, and so depending on if it's going to be expensive or dangerous to make a type 1 error, then you can adjust your alpha level, let's start calling it, right? The type 1 error rate. Okay, so the type 2 error, when I don't have enough evidence to reject H0, but it actually should be rejected, well, one way that I can do that is, or the only way that we will have to do that is to increase our sample size. Okay, so the type 2 error rate, or the type 2 error, the only way that we can control the type 2 error rate is by changing the sample size, increasing the sample size. Okay. We can control the type 2 error rate by increasing the sample size. What happens when we increase the sample size? If we increase our sample size, our margin of error gets smaller, right? So then we get more precise estimates. We don't have this huge spread. Oh, I don't know what's going on here, right? We kind of have this more precise estimate, and then we would have more evidence against H0. Okay, and so if we look at our interval, p hat plus minus z star times the root of p hat 1 minus p hat over n, right? If I increase this, then what happens? Well, the p hat, I've already collected my sample, so it gets weird. I can't really change the sample size, but in theory, if I increase my sample size, and presumably the population or the sample proportion would kind of hold steady, right? We know it hovers around some value, so that's not going to change. And so this whole square root chunk is going to decrease, right? I'm dividing by a larger value, so I'm going to decrease that. And then my Z star stays the same. So if I increase the sample size, then this decreases, right? Which means that my interval is going to be more precise around the estimate. The interval becomes more precise around the estimate. Okay. In terms of an example where we can kind of wrap our head around it, right? If you're thinking about someone who is who's been arrested, and we're in court, there's two decisions that can be made, right? So a person is either innocent, right? Which would be, let's say H0, oops. Try not to draw all over this thing, right? So the person is innocent or they're guilty, right? There is some truth and we don't know what it is. They might tell us something, two parties, they argue their points, right? And we have to make a decision, right? Let's say we're jurors and we make a decision, I don't know. So we either say, nope, this person is guilty, right? Or not guilty, right? But there are mistakes that can be made along the way. So what I'm going to do is I'm going to replace this. I'm going to copy it, and we can consider the two types of errors in a court case scenario, right? In a court case scenario. So here, I'm going to paste this here. Oh, hey, that's weird. How about that? And maybe, because I can, make it bigger, so I have more room to write. Okay. So what we said was, okay, let me see if I can find a color that's going to work. Maybe blue. So H naught is true, right? The person is not guilty, right? So person is not guilty. Oops, that doesn't even remotely look like guilty. There. Or H naught is false. Why is the H naught is true? If H naught is true, well, H naught has to be a statement of no change. We have to assume that they're not guilty until we have proof otherwise, right? And so that's going to be our H naught. And then if that's false, then we would say that this person is guilty. Right? Here, my conclusion, if I reject H naught, then I'm saying that the verdict is that they're guilty, right? Send them to jail. Whereas here, oops. If I fail to reject H naught, this would be a verdict of not guilty. So in terms of not guilty, guilty, a type 1 error is when we send someone to jail even if they're not guilty, right? We give them a guilty verdict when they're actually innocent, right? So sending an innocent person to jail, you can see how you would want to reduce that type 1 error depending on the scenario, right? Of course, not all scenarios are this grave, right? You're not always sending people to jail based on this stuff. You might be making decisions like, oh yeah, this tomato plant did produce more than this other tomato plant. Then it doesn't really matter, right? So there's kind of layers to how you decide what the type 1 error rate should be, because remember, that's the one that we can control easily. A type 2 error in this case is basically letting a guilty person, because the person is guilty, but they get a verdict of not guilty. So those are our two outcomes. So a type 1 error in this case is an innocent person is sent to jail. And a type 2 error, a guilty person walks free. Okay. So depending on how dangerous or expensive it is to make a type 1 error, we're going to adjust our alpha level, right? Because that's our type 1 error rate based off of that. Okay. And so the type 1 error rate is the alpha level. Okay, we called it alpha, but we'll call it the alpha level. Okay, and depending on how dangerous or expensive it is to make a type 1 error, we will adjust the alpha based off of that. So the type 1 error rate is the alpha level, and we will adjust it depending on how expensive or dangerous it is to make a type 1 error. Depending on how expensive or dangerous, might be dangerous, it is to make a type 1 error, right? How expensive or dangerous is it going to be to send an innocent person to jail? Well, that's really bad. So we want to make sure that that's not what we're doing, right? We also just want to make sure that a guilty person doesn't walk free. Yeah. And so that alpha level comes with a little bit of baggage, right? Because it is the type 1 error rate. I'll highlight that here. Okay. So the type 1 error rate is the alpha level. Okay. Let's see here. So we said that one shortfall of using a confidence interval is that we'll only be able to detect a change. We'll only be able to talk about a change. Now we might want to talk about, this proportion is less than another proportion. But another problem with using a confidence interval for hypothesis testing is that we can only extend it to a difference of 2 proportions. So here we've looked at one proportion compared to another hypothesized proportion. So just a value, right? Some null value. The other one, so the extension that we're going to make is we're going to say, okay, well, what if we want to compare 2 sample proportions? We'll still be able to do that. But after that, we won't be able to build a confidence interval anymore. And so that's where we tap out. But we definitely want the tools to be able to compare more than 2 proportions. Okay. And so another shortfall of using confidence intervals for hypothesis testing, is that we can only compare one sample proportion to a null value, is that we can only compare one sample proportion to a null value, or compare 2 sample proportions, right? But we can't compare more than 2 sample proportions, or compare 2 sample proportions to each other. That's in the next chapter. Okay, so we're going to get there, right, where we have 2 sample proportions. Now we actually just want to compare them against each other. Okay, so we want tools, or we'll need tools that extend to multiple proportions, more than 2 proportions. Okay, so we will need formal hypothesis testing tools to compare more than 2 proportions. Okay, that's fine. But that's kind of where using a confidence interval ends, and then we'll rely more on the p-value approach. So, okay, we've talked about this p-value approach. Now let's get into it. So the p-value approach, oops, that doesn't say approach, to hypothesis testing. I'll put in brackets that it's a more formal approach, and it's kind of typically how we introduce hypothesis testing. We don't typically start with a confidence interval, but I think this kind of makes the connection a little bit nicer, so that's good. So the p-value approach, now, what's going to change? Well, the p-value approach, we still use the same steps for hypothesis testing because we're still hypothesis testing. But now what I want to do is I want to go through each of those steps again and look at how things are changing. Okay, because we've seen how we do it with the confidence interval, and so now we're doing it with the p-value. The p-value, by definition, let's define the p-value first, so it's not just this crazy p-value. What's confusing is there's so many letters floating around. There's p's and z's and z stars and q's and n's and all kinds of things, right? But the p-value is the probability of seeing something as extreme or more extreme than what you saw, assuming the null hypothesis is true. Okay, so by definition, the p-value, it is a probability, and it's the probability of seeing a statistic as extreme or more extreme, as extreme or more extreme than what we saw, assuming the null hypothesis is true. So going back to that little caveat that we said, okay, well, we actually do all our testing assuming the null hypothesis is true until we see that, okay, this is pretty extreme compared to what I thought was going on here, right? And then that gives me enough evidence to reject H naught. So it's the probability of seeing something as extreme or more extreme than what we saw, assuming H naught is true. Okay, so I'm going to underline that because that's going to be really important, right? Because we do all our testing assuming the null hypothesis is true. We do all our testing assuming H naught is true. Okay. So that's going to be important, right? So just remember, through every step, you assume H naught is true until you have proof otherwise. Okay. There are a couple of little nitpicky things that change because now I'm going to have some hypothesized proportion. And so we had that in the confidence interval case, but we still use the standard error was just based off of the sample proportion. So now, if we're using the p-value approach, just a couple of things change. How we calculate the standard error changes just slightly, and how we check the conditions changes just slightly. Okay. So when using the p-value approach, And it doesn't really matter as long as you remember at this point, you know, you're only human, you can't remember all the different components. But at this point, as long as you remember that you have to treat them differently. But the reason is because we are assuming that the null hypothesis is true. And so now we're relying a little bit more heavily on that. Okay, and so that's where it comes back to. But when we're using the p-value approach, we make a few adjustments. Okay, the first one is that the standard error of p hat is now going to be the square root of p naught times 1 minus p naught over n. Okay, versus before, right, for our confidence interval, we were checking whether, or we were finding our standard error as p hat times 1 minus p hat over n. Right, so that's important. I'm going to highlight here. Sometimes it just has a p here for the population proportion, but remember, H naught is saying that P equals P naught, and we're assuming that that's true, right? And so sometimes it'll just be just a P here. Oh, losing my pointer, right? And so P equals P naught in the one sample case. And so I like to emphasize it with a P naught here, right? Or it might just say P times 1 minus P over N, right? And this is just, we assume H naught is true, right? And so now that's what's going in here. Technically, it's the population proportion, the hypothesized population proportion, but I just find that it's a little bit helpful if we write the P naught, because we're assuming that P equals P naught, right? P naught is the value, so that makes it a little bit easier. Okay, so that changes. And the other thing that changes is that when we check our assumptions for normality, we no longer use the p hat, which is the observed number of successes versus the observed number of failures. Now we're checking against the hypothesized number of successes and the hypothesized number of failures. Okay, so here's kind of the first adjustment. And then the second adjustment is when checking the normality condition, we check to see that our, I'm fumbling for the words here, we check to, I still want to say to see, it doesn't sound very good. We check that, still doesn't sound good. We check that the hypothesized or the expected number of successes and failures is more than 10, that the expected number of successes and failures is more than 10. Now, here's where it gets right a little bit tricky, is because if you're taking data science with me, then they're using 5, but I would prefer it if you just stuck with 10 all the time. But we can be a little bit flexible. It's always going to be satisfied, so it doesn't really matter, but we still have to check it, right? And so the normality condition becomes, so for the p-value approach, we have to check that n time, oh, it's really annoying. N times p has to be greater than or equal to 10, and n times I'll do 1 minus p, but so this is actually the expected number, assuming the null hypothesis is true. Expected number of successes and failures, assuming H naught, H naught, which says that P equals P naught, is true. Oh, expected there. Which means what? It means that P equals P naught. So really what we're doing is we're saying, right? Or we can write N times P naught has to be more than 0, 10. And N times 1 minus P naught has to be more than 10, right? Versus the confidence interval, right? If we're doing a confidence interval, then we were checking against the actual number of successes and failures, which if you have just N and P hat, then you can calculate it that way. Or if you have the explicit successes and failures, you can just use that. But just for symmetry, I'm going to use N times P hat has to be greater than or equal to 10, and N times 1 minus P hat has to be greater than or equal to 10. Right. And so here, these are the observed, and maybe I'll give myself some room here. Observed successes and failures. And this is really annoying in the beginning, but it's one of those things that you just need to kind of commit to memory. And of course, your guys' tests and stuff is all open book, so have it organized for yourself somewhere along the way, right? And as we do more examples, you'll see. The independence condition is still there for both scenarios, right? So we have to check, do I have enough successes and failures, whether that be observed or expected, but I also have to have independent outcomes. Anything else before we start with the actual outlining the approach? So when we're using the p-value approach, we have to make these 2 adjustments. Okay, they're not major, but they're going to make a difference if you're trying to enter your answers and you've used a different standard error. For example, if you've used the one for the confidence interval, that's going to be marked wrong. What's going on here? Okay, let's outline the steps to the hypothesis test. Steps to a hypothesis test with the p-value. Okay. So step 1 is still going to be to set up your null and alternative hypotheses. And so that's going to be the same regardless. And so set up hypotheses. H naught is that P is equal to P naught. And for now, I'm going to have HA, P not equal to P naught. Okay, we'll be able to change that this inequality later. Okay, but for us, we're always just going to keep an equal sign in the null hypothesis, just to emphasize that it's a statement of no change. And then any adjustments that we make, we're going to make in the alternative hypothesis. You might have seen that in the null hypothesis, we have greater than or equal to, less than or equal to, but notice how there's always the equal sign there. So we'll forget about the other side, we'll call it. So we will be able to change this right, later, right? It's going to be either not equal to, less than, or greater than, depending on the question. Depending on the question. Okay. If you're looking for a default, though, the default is going to be this not equal to. Okay. Okay. So that's going to be our default. If you're ever not sure, use the not equal to. It's going to be safer because it's just a statement of change. You're not saying that you have some knowledge about the sample. Right. Okay, so that's going to be the same. Step 2 is when we do the test, right? So before, that's when we calculated our interval. Now we're going to calculate a test statistic. Step 2, calculate, or I'll say do the test. That's usually what I have it kind of summarized as. And so for the p-value approach, we're going to calculate the test statistic for one sample proportion. That test statistic is going to be a z-score. We know how to do that, right? We just haven't used it in this context. And yes, that's the reason you have to practice so much, right? And so z equals p hat minus p naught over the root of p naught minus, oh, sorry, not minus, times 1 minus p naught over n, right? That's the standard error of p hat. Okay. So point estimate, how far is it from the hypothesized value, taking into account the standard error of that p hat, right? That's the spread of p hat. Okay. So here we're seeing how far is the sample proportion from the hypothesized proportion, taking into account the spread of the sample proportion. Taking into account the spread of the hypothesis, or sorry, of the sample proportion. Right, so that's what we're calculating here, right? How far is that sample proportion? If I assume that H naught is true, which says that P is P naught, then how extreme is this sample proportion, right? So it's going to end up somewhere in a tail somewhere, probably. So now in step 3, oops, I had to generalize it as gather evidence, but it's really in a p-value approach, it's going to be find the p-value. Gather evidence. So this is where we find the p-value. Okay. So in terms of our normal distribution, and of course, before you do any of this, you have to check the assumptions. I guess I should have made that a step 0 or something, but I'm assuming that you've checked the assumptions, and now we're just talking about the actual hypothesis test. So find the p-value. If we have some hypothesized proportion, it's going to be centered on p naught. Okay. And then what we're going to have is we're going to have some, I'll use light blue here. We're going to have maybe some p hat here, right? A sample proportion. Notice that it could have happened somewhere on the lower end as well. 2 viewers today. So I've got p hat, but p hat could have happened over here, right? And so that's what I'm allowing when I'm testing a two-sided test. So when I'm looking for a difference, right, I could be looking in either direction, either tail. Okay, and so here, this, right, once we take into account the spread that we're expecting to see, then we say that, okay, remember the p-value is the probability of seeing something as extreme or more extreme than what you saw, right? And so here, this is going to be the p-value. We call this a one-sided p-value. Okay. The two-sided p-value is when we say, okay, if I'm testing a not equal to scenario here, right, I'm just looking for a change. So just because I saw something up here, right, I saw a sample proportion that was above, that could have just as well happened on the other side as well. So now I'm going to try something weird here. Okay, so it could have happened here as well. I've got this like ghost p hat, and those are supposed to be symmetric. And right, so this p-value could have happened on this side as well, one-sided p-value. Hey, cute. Hard to read, but I'll fix that. I think I like that one. Okay, and so for when HA is that P is not equal to P naught, the sample proportion will only appear in one of the tails, but we need to consider it could have happened in the opposite tail as well. The sample proportion, oops. Will only be in one tail, but we need to consider that it could have happened in the other tail as well. But we need to consider that it could have happened in the opposite tail as well. Okay. And I'm totally running out of time, but let's see here. Step 3, step 4. So once I have a p-value, we know how to find a p-value because I can use, if I have a z-score, right? And so how do I find this p-value? Well, I use my z-score to find the area in one of the tails, right? And so, oops. From step 2, we have a z-score. So we can use software, but in this case, I'm going to assume that we're still using the tables. It's old school, but whatever. So from step 2, we have a z-score, so we can use the z-table to find the one-sided p-value. Then multiply it by 2. I know I'm out of time. Then multiply it by 2 to find the area in both the tails. To find the area in both the tails. Okay. I'll leave it there and we'll continue this list next day. I keep doing that, but I guess that's how it goes. If you have any questions, let me know. Otherwise, I'll see you on Thursday. Weird. Stop this here.